Hi everyone. In this video, we'll be talking about Dijkstra's algorithm, one of the most popular algorithms for finding the shortest path between two nodes in a graph. So how does Dijkstra's algorithm work? The algorithm works by starting at the source node and visiting all the other nodes in the graph in order of increasing distance from the source. The algorithm uses a greedy approach, which means that at each step, it chooses the next node to visit based on the minimum distance from the source node. The distances are updated for each node as the algorithm progresses, and the algorithm continues until all nodes have been visited or the destination node has been reached. There are some key concepts you need to know in order to understand the algorithm. A graph is a collection of nodes and edges. In Dijkstra's algorithm, the graph represents the map of the network, and the nodes represent the locations and the edges represent the paths between them. A weighted graph is a graph in which each edge has a weight or cost associated with it. This cost represents the distance between two nodes. A priority queue is a data structure that allows you to insert elements in order of priority. In Dijkstra's algorithm, the priority queue is used to determine the next node to visit. The shortest path is the path between two nodes with the minimum total cost or distance. In Dijkstra's algorithm, the shortest path from the source node to the destination node is found by updating the distances of each node as the algorithm progresses. We start by defining the Dijkstra function that takes as input a graph represented as an adjacency list, a start node, and an end node. In this line, we create a dictionary distances to store the distances from the start node to each node in the graph. We initialize all distances to infinity as we have not yet calculated any distances. Here, we set the distance from the start node to itself to 0. This is because the distance from a node to itself is always 0. We also create a dictionary previous to store the previous node for each node in the path from the start node to the end node. We initialize all values to none as we have not yet found any paths. We create a list visited to store the nodes that have already been visited. Initially, this list is empty. We repeat the following steps until all nodes in the graph have been visited. We find the node with the minimum distance that has not yet been visited by calling the find_min_distance function. If the current node is not the end node, then we search for the next nearest neighbor node. For each neighbor of the current node, we check if the new path through the current node is shorter than the previously known path. If it is, we update the distance to the neighbor and the previous node for the neighbor. If the new path through the current node to the neighbor node is not shorter, then we continue with the for loop. Else we update the distance to the neighbor node by adding the distance from the current node to the neighbor node to the distance from the start item to the current node. We also update the previous node for the neighbor node, which is later used to return the short's path. We continue the for loop until we have processed all neighbors. After the for loop has been finished, we add the current node to the list of visited nodes. And continue with the while loop. If the current node is the end node, then we have found the shortest path from the start node to the end node. We create the resulting path from the start node to the end node by calling the function build_path. And return the distance from the start node to the end node and the path from the start node to the end node by calling the build_path function. The find_min_distance function takes as input the distances dictionary and the visited list and returns the node with the minimum distance that has not yet been visited. We initialize min_distance to infinity to keep track of the minimum distance that has not yet been visited. We also initialize min_node to none to keep track of the node with the minimum distance that has not yet been visited. For each node in the distances dictionary, we check if the distance to the node is less than min_distance and the node has not yet been visited. If so, we update min_distance and min_node to the distance and node, respectively. If the node has not been visited and the distance is less than the minimum distance, then we update the minimum distance and the node with the minimum distance. and continue with the for loop. After we have processed all nodes, we return min_node as the node with the minimum distance that has not yet been visited. The build_path function takes as input the previous dictionary, the start node, and the end node, and returns the path from the start node to the end node. We start by creating a list that stores the path. Then we set the current node to the end node. We repeat the following steps until the current node is the start node. First, we add the current node to the path. Then we set the current node to the previous node. And continue with the while loop. After we have reached the start node, we add the start node to the path. And return the path in reverse order so that it starts with the start node and ends with the end node. And that's it. This was a brief overview of Dijkstra's algorithm and its implementation in pseudocode. Thank you for watching, and I hope you found it helpful.